Greetings. Welcome to our lecture series on slope deflection method. In this particular session, we will be discussing upon some standard case of fixed beam. Already we have gone through the derivation of these fixed end moments for the beams. So let us say first case fixed beam with a central point load where the load is provided at the mid span of the beam. A and B ends are fixed support. That's why the behavior of the beam will be having a hogging moment. The moment at A will be anti-clockwise and moment at B will be clockwise. The moment at A will be equals to minus WL by 8, where I'm going to write it as a MF A to B. F stand for your fixed and A to B is going to stand for the joint where I am going to measure the moment and in direction I am going to move. So I am looking from A towards B. That's why I am writing it as A to B. Hope you will remember this one for the other cases. I will not repeat this for further cases. The F B to A means I am at a joint B and looking towards A. The moment will be positive because we have considered this one as a clockwise positive WL by 8. Now the second case is fixed beam with eccentric load. Means here the load is placed at a eccentric distance. Let us say it is at a distance A from left hand support and B from the right hand support. In this case, moment at the end A, MF AB will be equals to minus AB square by L square. We can remember this with a relation like it will be 1 times the near end and square for the far end divided by span square. In the similar fashion, if I write B to A, we can write it as a W A square B divided by L square. Now A is here the far end, that's why A square will be there, and near end is B, that's why B will be in a single multiple. So we can write it as a W A square B by L square. Now let's move to the second case. It is a fixed beam with uniformly distributed load. Means here the load is uniformly distributed over the entire span. Let's say its magnitude is W kilonewton per meter. Since the uniform distribution is there, the moment at both ends will be of a similar magnitude. We can write it as a MF A to B equals to minus WL square by 12. MF B to A is equals to plus WL square by 12. Now we'll go towards a case fixed beam with a uniformly distributed, uniformly varying load. Means here the load is going to have a maxima and minima value. At one end it will have a minimum value, at the another end it will have a maximum value, or we can say it will have a gradually increasing load towards from one end to the another end. That's why name is given as a uniformly varying load. In such a case, moment at the end A will be given by the relation minus WL square by 30 and moment at the end B will be given by the relation plus WL square by 20. Now let's go towards the next case where the beam is subjected to eccentric couple. The couple is placed at eccentric distance over the span. So due to this, the moment generated at the end A will be equals to minus MB by L in bracket 2 minus 3B by L. Similarly, the moment at B will be given by the relation MA by L in bracket 2 minus 3A by L. If we relate here, when we consider A joint, the multiplier in the bracket is B here. Whereas if I consider the B joint, the multiplier with the moment is in the bracket is A here. This we have to remember to recite the formula. Next to that, we'll consider the case fixed beam with a 2-point loads, where the beam is subjected to 2-point load. Let us say the distances for this instance are symmetric. So if I say the left hand load W, load towards the left hand side, it at a eccentric distance A. Similarly, from the right hand side, it is also at a eccentric distance A. Now, due to this symmetry loading, we can say moment generated at end A will be equals to minus W A into L minus A by L, whereas at B will be plus W A into L minus A divided by L. Magnitude will be same, but direction will be opposite because of the sign convention, where we consider the beam fixed beam is will have a hogging type of a moment. So one side it will be clockwise, another side will be anti-clockwise. Please remember these formulas because we need to apply this directly while solving the numericals uh, on fixed beam using slope deflection method. Thank you. We'll meet again in next lecture. Thank you.